So today we will discuss about stress on inclined section and this is okay. Yeah. So in the last class we discussed about strain energy due to axial load, like how the strain energy is calculated, and we are restricting only to axial load right now because we have studied only axial load. In the next coming class we will be dealing with bending, torsion, and load. So in that while we are dealing with that section, we will study about strain energy due to bending, torsion, etc. So today we will deal about stress on inclined section. Okay, so before that, yeah. So the screen is visible, right? This paint screen. Hello.
So there is a white screen visible, sir.
Yeah, fine. That's true.
Thank you, sir.
Okay. So what we are going to study now is stress on inclined plane. So till now, what we have studied is like we considered a cross section which is perpendicular to the axial load, right? For example, like we considered a prismatic bar, and then we assume that there is a tensile load acting on this bar, and then as I said, like I am taking a cross section perpendicular to this cross section where the tensile load is acting. So we made some assumption that the bar is prismatic, the material is homogeneous, axial load acts as the centroid. These are the three assumptions which we have made. The bar is prismatic, material is homogeneous, and the third one is the axial load is acting at the centroid. Through the centroid act. And at the same moment, we made another assumption that okay, the cross section or the plane which we are considering, that plane is exactly perpendicular to this load, the load which we are applying. So now, so if we consider the three-dimensional structure, it will be something like uh, so this is the plane which we are considering, so the cross section which we are considering, and we assume that in this cross section, this is a cross section, the stress distribution is like this, sigma x, and which is given as A by A, where A is the cross sectional area. And now, okay, so this is fine. This is we have studied till now. So now what we are going to do here is instead of considering this plane of plane cross sectional plane, we consider a cross sectional plane inclined with respect to some angle. For example, like okay. So I'm badly drawing these figures. I will try to make it. So I'm just considering. Okay, I will consider instead of 3D structure, I will consider 2D structure. So that will be easy for me. So so this is my inclined section here. And how do we measure this inclination? Inclination is measured with respect to a normal or the outward normal from the plane. So this is the outward normal, and this is the horizontal axis, and this is theta. So ensure, like I want to ensure that theta is not measured with respect to the tensile load acting. It is measured with respect to the angle between the outward normal and the longitudinal axis. So this is the outward normal n, which I am respecting, and the longitudinal axis. This is the x-axis. So this will be the theta. So basically, it means that there is a plane which inclined at an angle theta with respect to the longitudinal axis. So in this case, we can see that. Okay, I'll again go into window. So we have a stress. We have a load acting here, and we are assuming that there is a stress distribution here. So the resultant of this stress, all the forces is the capital B. Okay, and now this. Okay, again I made a mistake. It's inclined plane. So what can we do with the, in this case, if we have a in this case for this without inclination with a cross section perpendicular, we define stress which is perpendicular to this cross section. So we got the sigma x. Similarly, in this region also we can resolve these forces along the surface as well as perpendicular to the surface. So let us call as let it be n, let it be v. So n is the force component from the p perpendicular to the inclined surface, and v is the component along the surface. So what can we say about the relation between n, p and v?
V square equal to n square plus v square.
That's true. So from that we can get n equal to e cos theta and v equal to p sin theta. Okay. So if I am considering this cross section, suppose this cross section is denoted by say a. This cross section, okay, sorry, this one. This is by say a1. This angle is theta now. So what can you say about this angle? Can someone be some? What can you say about this angle? The angle which I have just drawn here.
That will be theta, sir.
The theta.
Yeah, theta. So basically, theta exactly. This is a usual easy way of denoting, fixing the angle. Like the angle between two lines is, if the angle between two lines is theta, then the lines drawn perpendicular to those lines, angle between those lines also will be theta. Like already this angle between these two lines are theta, so we are drawing the lines perpendicular to them, so between them also the angle will be theta only. So now we can write as this. We can get a relation equal to a equal to a1 cos theta, and from that a1 equal to a by cos theta. Now in this surface, so this is the line, this region, this is the section plane. We are drawing one force perpendicular to the section and one force parallel to the section. So we have studied what is normal stress and shear stress. So normal stress is defined with respect to like perpendicular to the cross section, and shear stress acts along the cross section. So in the same way we can define here a stress components like normal stress as well as the shear stress here. But it is not with respect to the sigma x. So I'm giving another notation sigma theta and tau theta here. Just want to ensure that in this case, the first one here, when we take a cross section perpendicular to the applied load, only we had the normal stress. The shear stress was coming as 0 here. But when we take an inclined section, when we resolve the original tensile load into two parts, we will get a normal stress as well as shear stress along the inclined section. So what can we say about sigma theta and tau theta in terms of P? Sorry. Sigma theta is nothing but sigma is stress is calculated as force by area. So here sigma theta will be
P by A cos.
yeah, normal force divided by the area here. So area of here is area of inclination A1. A1 is this area, cross sectional area. So n is given as P cos theta by area of cross section is A1. A1 is nothing but A by cos theta. It will come as cos square theta. And we can do a substitution like cos square theta in terms of cos 2 theta. So it will be like cos square theta is what 1 plus cos 2 theta by 2. So we can write it here as P by A. I'm just giving 2 here. Then 1 plus cos 2 theta. Okay. And here I make the assumption that I'm just assuming this sigma x equal to P by A here. Okay. Not assumption, like I'm taking this value sigma x equal to P by A, and if I substitute here, I'm getting sigma x by 2 into 1 plus cos 2 theta. So this will be the stress perpendicular to the inclined section when an axial load P is acting, where sigma x corresponds to the normal the force by area and like when there is no inclination. And similarly, we can define what is called the shear stress here, tau theta. Tau theta will be the force along the inclined section, that is V by the cross sectional area. And V is nothing but P cos theta by A1. A1 is A by cos theta. Sorry, this is sin theta. No. Something wrong. Sorry. V is P sin theta by A1. A1 is A by cos theta, so it will come as cos theta. I'm just multiplying and dividing by 2, and I'm just making P by 2A sin 2 theta. Okay. And here again P by A, I'm just giving the assumption sigma x. So it will come as sigma x by 2 sin 2 theta. Okay. Now, then what you have to do here? Okay, I need to talk about the sign convention. So if the outward normal vector to a plane is directed to a positive axis, the stress components in the plane is said to be positive if they are along the positive axis. Similarly, if it is negative, then again it is negative. So what does it mean? Suppose if I am taking if I am having a cross section like this on this, so this is my x-axis, this is my y-axis, and this is my one force, this is another force. If the outward normal vector to a plane is directed to a positive axis, so this is the outward normal vector, it is directed to the positive axis. So x-axis, okay. So this is my centroid, okay. Not this, the center point. So this will be considered as positive, and this is also will be positive. So what can you say about this line? Will it be positive or negative?
Positive.
Why it is positive? It is actually negative in the sense it's like yeah. See, the outward normal vector to this plane, it is not to the positive direction. It is to the outward normal vector will be in this direction only, like which I have drawn here. Then in this direction, the stress components is again to the negative direction, right? Okay, I will make another figure. What can you say about this? This will be the shear stress. Okay, I will make one by one. This is fine, right? The outward normal vector is always to the positive direction, and the stress component is also is positive if they are along the positive axis. And now there is a shear stress coming here. What can you say about this shear stress? So this is the outward normal vector, which is directed to a positive axis, x-axis. And now stress component is said, so I want to say what is the sign convention for this. It is said to be positive if they are along the positive axis. This is along the positive axis because our positive y-axis is to the upward direction, and this is what we are giving. So this will be positive. What can you say about okay, ineffectively like a positive sign convention? Okay, as I said before, it is actually positive coming. Okay, well, the total sign convention, if I am writing here, it will be positive. Then there is a shear stress acting like this, and then this is a shear stress. So this is positive. Okay. Now the reason why I said that because our sign convention is like taken like this is positive, then this is positive, and then yeah. Okay, let's take up to this point. We don't need to think about this right now. So what will be the value for tau theta right now? Whether tau theta is positive or sigma theta is actually positive here because it is the outward normal. If you consider the outward normal as in positive direction, then we can see that sigma theta is actually a positive quantity. What can you say about tau theta here? Tau theta will it be positive or negative as per the sign convention?
Negative, sir.
Yeah, tau theta will be negative. So in our values, the absolute value we are denoting by tau theta sigma x by 2 sin 2 theta, but in effect it is actually a negative direction. Okay, so when you report, you should either you should show the sign convention in the figure, or when you if you are giving a figure like this, the same figure sigma theta, and if you are plotting a diagram like this tau theta, then you should report the value as negative only here. This is positive. Or otherwise, if you are if you want to report a positive value, then you should change this to the opposite direction. Yeah. So now we will try to plot this theta versus what is the value of sigma theta as well as tau theta versus theta. Okay, so I will just take some arbitrary value, say theta equal to 0, pi by 4, pi by 2. I need to find sigma theta and tau theta. So sigma theta is given by this expression, tau theta is given by this expression. So someone can you give me what will be the value for sigma theta when theta equal to 0?
0.
Okay. What will be value for
It
tau
will be
theta?
sigma x. It will be sigma x, sir. Sir, at theta
Yes.
equal to 0, the
Yes, yes. So it will be sigma x. And what will be the value for tau theta here?
0.
0. For pi by 4.
Sigma x by 2.
Sigma x by 2. For tau theta.
Sigma x by 2.
Sigma x by 2. Fine. But at the same time, we are assuming the sign convention here. Okay, so it will come as minus sigma x by 2. Okay. Is that fine? Like, because we are just taking the sign. We are just applying the sign convention here. That's why I'm just putting minus sigma x by 2. Is that okay? Anybody has any doubt?
Yes, sir. Can you please explain that again? Why is
Okay.
it negative?
Yeah. So in the sign convention, we have said that if the according to the sign convention which we are following, we just assume that if the outward normal is to the positive x-axis or positive axis, then the stress components are said to be positive if they are also along the same axis. Okay. I will take the if the outward normal vector. So I am considering this AB as the one side of this plane. AB as one plane. This is the outward normal vector. Okay. This is along the positive x-axis. So this first criteria is okay. Then I am assuming that what can be the stress components here? There can be like stress components like this. There can be sigma 1 can be like this. Sigma 2 can be the opposite direction. Sigma 1 can be positive if they are along the positive direction. Okay. If it is along the opposite direction, then it won't be positive. It is negative only. So this sigma 1 is positive, sigma 2 is negative here. And now similarly, along the plane I am considering some say tau 1, tau 2. So what can you say about tau 1 and tau 2 in the same sense? Here the outward normal vector is along the positive axis. The stress component is in this plane. It is positive if they are along the positive axis. So this will be positive. And tau 2 is in the negative direction. So this is negative. And now if you try to now this portion and this portion, if you try to incline, this is what similar to we are getting. This will be like tau 2 and this is our, tau theta, this will be our sigma theta. So that's why I said sigma theta is okay, positive here, but tau theta is actually like a negative quantity. It's assumed as a negative one. Clear now?
Yes, sir.
Okay. And now for pi by 2, what will be the value for sigma x? Sigma theta and tau theta.
Sigma theta 0, sir.
Okay. Tau theta. Tau theta will be sigma x by 2 sin 2 theta into pi by 2. What will be the value for tau theta?
It will also be 0.
Yes, exactly. Now we will plot this sigma theta and tau theta versus theta. For simplicity, I'm just, so this is theta and this is pi by 2. Sorry, this is pi by 4, this is pi by 2. Okay, for sigma theta, it will come like, for pi by 4, it is coming as sigma x by 2. Okay, so we'll get 0, okay, for this one sigma x. So 1.40 it is sigma x, for pi by 4 it is sigma x by 2, and for pi by 2 it is again 0. And if you take minus pi by 4 and minus pi by 2, that you can calculate, but it will come out.
Sir.
Yeah.
Sir, but logically, when it's pi by 2, we should have it. We should have a shear component, no, sir. Like when we apply the load of P along x-axis, and we have a surface perpendicular to the load, then we'll have shear component, no, sir.
Yes, that's correct. But at the same time, we need to consider which cross-sectional area you are considering. Because at that cross-sectional area, the that part will be 0. The other one. I got your point. Like if you any concept, okay. His point is when theta is equal to 90 degree. So this is our theta equal to 0 cross section. So when you are making an angle, theta in the angle this one, and then when theta equal to 90 degree, the cross section is like this. So there will be, he's asking like whether there is a shear component is there, right?
Yes, sir. That's right.
Yeah, but we are considering when we consider the cross section, so at that time what will be the cross section? A1 by cos 90. So it is coming as like, or if you consider this A equal to the opposite way, A equal to A1 cos theta, cos 90 will become what? 0, and A1 will become infinity. Okay.
Sir, so that means there is no defined cross section at 90 degree.
Yeah, there is no defined cross section at 90 degree, and also we have to define on which area we are defining the stress and strain. Sorry, the stress, the normal stress and the shear stress. Okay. Okay. Yeah. So when we are plotting this, we will get like this. And now for the other one, for this is for sigma theta, and for the other one it will be at the 0 it will be 0, and then at sorry at the 0, yeah, this is 0, and then at pi by 4 it is minus sigma x by 2. Then again it is coming like this. And what can you say? Like this will be like this one. Okay. Okay. This figure will be something. It is correct. Okay. So this one will be sigma theta. This is tau theta. So from this, what's what type of conclusions we can make? See, when you compare the value for tau theta, the maximum value, sorry, sigma theta, the maximum value will be sigma x. Okay, so the maximum I will write here. The maximum normal stress equal to sigma x. And when it happens at theta equal to 0, and with increase in theta or decrease in theta, there is a change in sigma x. You can see this figure, like when increase, basically when this is the maximum value of that is happening at theta equal to 0, and with increase in theta or decrease in theta, there is a gradual decrease in the maximum value, the normal stress. And similarly, the regarding shear stress, what can we say? The maximum shear stress is happening at maximum. What is the maximum value for the shear stress? That is actually sigma x by 2, and the value it is when the angle of inclination is pi by 4, that is 45 degree. Okay, so I will draw a. So this is our some. This is our prismatic bar. I am considering two elements here. One is this element which is like without inclination, and I am considering another one which is inclined at say 45 degree. Is that fine? And then now I will draw an this is A, this is for A, this is for B. Okay, B draw first. Okay. So here we are having only the sigma x. There is no shear stress coming here. But for the element B, this is called the stress element B, which corresponds to the inclination, which is inclined at an angle 45 degree. We can say that there is a sigma x by 2. That is a maximum. That is along the sigma theta. There is a shear stress. For shear stress, I am just giving not a full arrow, just a half arrow only, just for notational representation. Tau theta is nothing but sigma x by 2. Okay, so what can you say about the forces here? Like on this plane, what will be the sigma x and tau theta? You just need to put just add so sigma, this one sigma x by 2, sigma theta and tau theta. These values are for at theta equal to 45 degree, and now for other planes you just need to add say theta 1. So this is theta 2, it will be 90 plus 45 degree, like that. So it will be like can get one more. You can incline to the opposite direction. So maybe like theta 3 might be like minus 45 degree, and theta 4 will be minus 135 degree. And when you substitute the values into these two expressions, sigma theta and tau theta, finally I will just plot the figure here. I will make the line. So we will get this as sigma theta. This is also tau theta. Then here tau theta. Then yeah, this is complete. Yeah, this is complete now. Yes. So this is sigma x, okay. Okay. I need to define one more term called complementary stress here. Complementary stress, and I think I have explained already, but explained in the sense like I didn't use the term complementary, but it is nothing but we have a two-dimensional. This is a two-dimensional representation of a bar, and we consider a plane at an angle theta. So complementary stress is defined with respect to a plane called complementary plane, which is nothing but a plane perpendicular to what we are drawing here. So okay, so this is perpendicular. So on this plane, whatever is the value, for example, like whatever value we are getting for the sigma theta and tau theta, these are called complementary stresses and complementary normal stress and complementary shear stress. Okay. And then I'm just using the notation dash to differentiate between the original one which you have defined. So how can we get? Again, we just need to, if theta is the angle of inclination with respect to this, suppose this xy, and this is our x dash y dash is the complementary plane, then what you have to do is we just need to, the theta dash is nothing but theta plus pi by 90 degree. And then we need to substitute these values into our sigma theta and tau theta. So what can you say? So sigma theta, the original expression was p cos square theta by a, or I will use this expression, not tau theta term, just sigma theta is p by a cos square theta. So what happens if theta is changed to theta plus pi by 2? What can you say about that? Is nothing but sigma theta dash. So can you give me what will be the answer? This is the expression for the sigma theta along the plane xy. We need to find the sigma theta along the plane x dash y dash. So we have to make the assumption, we have to just incline by theta dash, I mean the original angle, we need to add 90 degree or more. So here I need to put p by a cos square theta plus pi by 2.
So P by A sin square theta.
Yes, p by a sin square theta. And similarly, what will be the value for tau dash?
Minus P by A sin 2 theta.
Okay, minus p by a sin 2 theta. If I are using 2 theta time, I think you need to put 2 here, the denominator also.
Sir.
Okay.
Yes, sir.
So what can you say about sigma theta and sigma theta dash now? Sigma theta plus sigma theta dash. What is that? P by A. Right. And similarly, tau dash is nothing but minus tau dash. Sorry. Tau dash is tau theta dash is nothing but minus tau theta. Okay, this is regarding the complementary stress. Now, illustration, but we will just have a small example. So, a metal block of 100 mm square cross-sectional area carries an axial tensile load of 10 kN. For a plane inclined at 30 degree with the direction of applied load, calculate normal stress, shear stress, and maximum shear stress. Okay, I will call one name, Devi Satvika.
Yes, sir. I'm doing.
Yeah. So let's start with, like, what will be the theta here?
30 degrees.
Actually, it will not be 30 degree. Just check the wordings of the question again and try to find it out.
Yes, sir.
Yeah. Did you get the answer? What is the value for theta?
60 degrees, sir.
Yeah, it is 60 degree. What is the reason?
Sorry, sir.
Okay, how did you get 60 degree?
It is inclined with the load at 30 degrees. So with the plane, it will be, with the horizontal, it will be 60 degrees.
So theta will be 60 degrees. And now what is the normal stress, shear stress and maximum shear stress?
Yes, sir. I'm calculating.
You can tell the formula, so meanwhile I will write it here, others can also calculate.
Yes. So sigma x is P by A.
We need to, sigma x is P by A, yeah.
So P is 10 kilonewton, 10 into 10 power 3 by A is 100 mm square. So it is 100 into 10 power minus 6.
We need to find the stress along the inclined plane.
Normal stress. Normal stress is sigma x by 2 into 1 plus cos 2 theta. So with the sigma x, we can calculate that.
Yes. So what is the value?
Yes, sir.
Okay. Thank you.
So theta is 0.25 into 10 power 5 Newton per meter square.
What is the value for normal stress?
0.25 into 10 power 5 Newton per meter square.
Okay, 0.25 into 10 to the power of 5 Newton per meter square. Meter square.
Yes, sir.
Okay. It will be nothing but 25. 1 second. 0.25 into 10 to the power of 5 Newton per meter square. Can you check the answer again? The units?
Yes, sir. 1 minute.
Others can also try this problem and just let me know if you are getting the same answer or not.
So it is 0.25 into 10 power 8. 10 power 8 Newton per meter square.
Temporary. Yeah, that's correct. So it is nothing but 25 into
25
10
into 6 Newton per meter square.
so Newton per meter square is Pascal, so it is come as 25 MPa.
Yes, sir.
And what about the shear stress?
Shear stress is 1 minute.
One,
0.43 into 10 power 8 pascals.
0.43 into 10 to the power of 8 Pascals. So in MPa, what will be the value?
Sorry, sir?
So in megapascal, it will be 43 MPa.
Yes, sir.
And what about the maximum shear stress?
Maximum shear stress is 0.5 into 10 power 8 pascals.
So what is in MPa, megapascal?
Yes, sir.
Yeah, what is the value in MPa, megapascal?
0.05.
Yeah, so 0.05 into 10 to the power of
0.05 megapascal.
No.
50 megapascal.
Yes. You should be very careful about the units, because once you are not putting like this, if you are not getting the correct answer like in the same, while reporting, then you will not get any value. That's
Yes.
the thing.
Okay.
So while calculating, like while starting the problem, you should write every notations and write the value, convert it in SI unit, then put it in the answer, and then try to do it.
Yes, sir.
Okay, then we'll move to the next problem. A prismatic bar of 500 millimeter square cross-sectional area is axially loaded with a tensile force of 50 kilonewton. Determine all stress acting on the element which makes 30-degree inclination with the vertical plane. So I will connect the name Dilraj Saini. Are you here? What about Ila Mohil? Jacob Thomas?
Yes, sir.
Yeah. So, can you solve this problem?
Yes, I'll try. Just give me 1 minute.
Yeah, you can start with the, like, I will write the variables, those things, formula and everything. Then everyone can also be a part. Yeah, just give me some values, like what is P, what is A, etc. The formulas which we have to use. Hello, Jacob. Jacob, are you there? Okay, are you there again? You are muted. I couldn't hear your voice. Okay, we'll move to next person. Kandesh Kumar. Kandesh Kumar, are you there? Okay. Then, okay, I have just some more minutes, so I need to wrap it. Padmasri. Padmasri, are you there? Hello. Okay. Ram Prasad. Hello. Is it because of any audio problem or?
Sir, yes, sir. I'm there.
Sir, no, you are audible, sir.
Okay, fine. So I think these people are not there, just log in and then left, right?
Sir, I'm there, sir.
Yeah, okay. Let's finish this problem. So what? Just tell me the values for P, A, theta, like that.
Sir, theta will be 30 degrees, sir.
Yeah, because here the element is making 30 degree with the vertical plane.
Yes, sir.
So
And
it is
here
like,
will be 500 meters, mm square, millimeter square. And tensile force will be 50 kilonewton.
It is 50 kilonewton, so 50 into 10 to the power of 3 Newton. Okay. And then what will be the final value? So no, not the final value. What will be? We need to find all the stresses. All the stresses means the shear stress, the normal stress, as well as the complementary part. So what will be the expression for sigma theta?
P by 2 into 1 plus cos 2 theta, sir.
P by 2. Okay.
P by 2a. P by 2a. P by 2a.
Yes. So what can you say about this value?
That will be P by 2a sin 2 theta, sir.
P by 2 sin 2 theta. Okay. Can you give the values for this?
Yes, sir. 1 second, sir.
Yeah.
So for sigma theta, it will be 56.2 megapascals.
I think there is something wrong. Can you check the answer again?
1 second, sir.
Sir, can you please explain me why theta is 30 degrees in this case?
Yeah, sure. So how do we calculate? Remember on the element which makes 30 degree inclination with the vertical plane. So we are just making
Sir, 75 megapascals.
yeah, 75 is answer. Calculate tau theta also and complementary stress also.
So tau theta is 43 megapascals and
Yes. This is it.
Yes, sir. Got it, sir. Got it. Right.
Understand. Yeah. Okay. Made me confused for a minute. That's why. So this is this is theta, and as I said, like we have to measure this angle. So when you draw a line, the angle between, suppose theta is angle between two lines, and if you are drawing a line perpendicular to these two lines, then the angle between them also will be theta. So this theta is measured as 30 degree, and we are just drawing a line perpendicular to both these lines. So that's why theta is coming as 30 degree. Okay, and then here the answer sigma theta is coming as 25 megapascal, and tau theta is coming as 43.3.
433, sir.
43.3, right? Megapascal. It will be 43.3.
Yes, sir.
Yes, sir.
43.3 megapascals.
Okay. And then finally we need to you can find the complementary stress as well as the shear stress. So sigma theta dash will be, I'm just writing the values here. Sigma theta dash will be 25 MVA. Tau theta dash will be nothing but the magnitude will be same as tau theta. So it is minus tau theta. So when we okay. So we just need to show it in a stress element. So what we can see here is this one will be the sigma theta. This is the tau theta, and perpendicular to that one. So that will be again this one tau theta. Okay. Sigma n dash and sigma theta dash and tau theta dash. Okay. And again, at the same time, I want to like you have seen like the cracks occurring in any bricks or in walls and all, and you have seen a pattern like it is appearing in like a 45-degree most of the time. So do you know what is the reason for that?
So the maximum shear stress is along 45 degree.
Yes, exactly. So in this case, the for example, like in ductile materials, for example, like if you take a chalk piece, and if you try to give a tensile force, and you can see like the crack pattern will be exactly 45 degree. And the reason why, because in ductile material, the failure due to tension is basically initiated by the shear stress. So failure will be occurring across that shear plane that is at 45 degrees. That's a point which I want to add. Actually, I forgot that. I need to tell that when I explain this figure, but I forgot that. And then there is a one more problem. Maybe you try to solve it. I will share the file here. So in the next class, if you have a doubt, you can tell me. Okay, so we'll wind up for today's class. I need to take the attendance sheet.
Sir, while saving this file, please keep the things which you have written, sir. Please don't discard it. Can you please do it, sir?
Okay. Yeah. Okay. I hope you are writing the notes in between.
Yes, sir, actually.
So that's the reason why I'm. Yeah, in the derivation, but I am keeping it, and this numerical example, I am just keeping the final values.
Okay.
And yeah, the derivation, everything I am keeping there.
Okay,
so
sir.
This one I am doing in a Paint. Okay, I will convert it into a PPT.
Okay, sir. Okay.
Yeah, sorry. I will download that sheet. Yeah, it's done. Yeah, thank you.
Okay, sir. Thank you.
Thanks, sir.
Sir, small